Imagine balancing a fully loaded 50,000-pound commercial fire truck.
Okay, that's heavy.
Right. But imagine balancing that entire truck on a piece of metal the size of a postage stamp.
Oh, wow.
Yeah. Human instinct tells you that the stamp, it just instantly turns to metallic dust.
Just completely flattened.
Exactly. But engineering tells us something entirely different. Like, we can actually use that tiny piece of metal to measure the truck's weight down to the exact ounce.
It completely breaks our intuition, doesn't it?
Yeah.
I mean, we're so accustomed to the idea that as technology shrinks, it just inherently becomes more delicate.
Right, like an old smartphone bending in your pocket.
Yeah, exactly. But when you're dealing with industrial physics, the physical footprint of our world minimizes, while the forces like gravity, pressure, weight, torque, they just remain absolute constants.
Which is the core paradox for today's deep dive. So, for you listening, we are heading into the invisible, hyper-precise world of force measurement.
It is such a fascinating space.
It really is. Specifically, we're looking at Interface Mini products and this whole expanding universe of miniature load cells. We're going to explore how these tiny sensors are basically the secret backbone powering everything from, like, delicate medical surgeries to heavy-duty aerospace testing.
The range is just insane.
It's crazy. Okay, let's unpack this. Because my first thought when looking at these 50,000-pound capacities on a miniature sensor was simply, how does the physical material not just fail catastrophically?
Well, what's fascinating here is the distinction between elastic deformation and plastic deformation.
Okay, break that down for me.
Sure. So when we think of metal crushing under a fire truck, we're picturing plastic deformation.
That's where it permanently bends or breaks.
Right. Exactly. It warps, it shatters, whatever. But load cell engineering relies entirely on staying within the elastic limit. Think of a diving board.
Okay.
You jump on it, it bends. You jump off, it snaps perfectly back to horizontal.
Right, it doesn't stay bent.
Yeah. Miniature load cells are constructed from these highly specific aerospace-grade alloys that are basically designed to have near-perfect spring properties.
Wait, really? So it's basically a highly tuned spring.
That's exactly what it is. It bends under immense weight, but we're talking about bending by fractions of a millimeter, and then it returns precisely to zero.
Okay, so the sensor isn't a rigid block, but that brings up the measurement aspect. Because if this tiny diving board is only bending a fraction of a millimeter under, tens of thousands of pounds of force,
Right.
how do you reliably translate that microscopic movement into usable data?
That happens through something called a strain gauge, and that's bonded directly to that metal flexure.
A strain gauge, what does that actually look like?
It's essentially this highly intricate microscopic zigzag pattern of metallic foil.
Okay.
And when the underlying load cell bends, that foil is stretched. Now think of a garden hose.
I'm with you.
If you stretch a garden hose, it gets longer and narrower, right?
Yeah, and that restricts the flow of water.
Bingo. The foil works the exact same way with electricity. As it stretches and narrows, it restricts the flow of electrons.
Oh, wow. So the electrical resistance goes up.
Exactly. And by measuring that precise change in resistance, you know exactly how much force is being applied to the metal.
Wait, I'm trying to picture the environmental variables here, though, because if we're measuring electrical resistance changes on a microscopic level,
Yeah.
wouldn't something as simple as the ambient temperature totally throw off the data? I mean, metal expands when it gets hot and contracts when it's cold.
That is a very real problem.
Right. Wouldn't this sensor think it's being crushed just because someone, turned the heat on in the factory?
That is a brilliant catch. And honestly, it was one of the earliest hurdles in precision force measurement. To solve it, engineers don't just use one strain gauge.
They use more.
Yeah, they use 4 of them. Arranged in a specific electrical circuit called a Wheatstone bridge.
A Wheatstone bridge, okay.
Yeah.
How does that fix the heat issue?
By placing the gauges in opposition to one another. So some are on the part of the metal that stretches and some on the part that compresses.
Ah, I see where this is going.
Yeah, they basically cancel out the thermal expansion. If the temperature rises, all 4 gauges expand equally. The voltage ratio stays perfectly balanced.
That is incredibly elegant.
It's brilliant. The system just ignores the temperature change entirely, registering only the actual mechanical force.
It essentially filters out the thermal noise.
Exactly.
But I still have to push back on the pure physics of the 50,000-pound load button. I mean, even with a Wheatstone bridge and aerospace alloys, 50,000 pounds is 50,000 pounds.
That's a lot of weight.
Right. Are you telling me this microscopic foil is taking the brunt of that?
Oh, not at all. And that's where the geometry of the housing comes into play. Think of a Roman arch versus just a flat plank of wood.
Okay, the arch is way stronger.
Right. But why? The strength of the arch isn't just the stone itself. It's how the shape routes the physical stress down into the pillars.
Oh, so the shape moves the force away from the weak point.
Exactly. Miniature load cells use incredibly complex internal geometries, what we call the load path.
The load path.
Yeah. The outer structure of the sensor absorbs and routes that massive crushing force entirely away from the delicate measurement zones.
Wow.
So the strain gauge only sees a highly controlled, predictable, microscopic fraction of that total load.
So they're engineering the stress path to basically bypass the delicate electronics entirely?
Exactly.
And this isn't just theoretical. Like, Interface has been doing this for a very long time. I was reading that they introduced the very first miniature load cells, the SM and SSM models, way back in 1974.
Exactly. 1974.
That's wild.
To put that in perspective, the microprocessor was barely in its infancy back then. Yet they were already pioneering this miniature precision force measurement.
They were way ahead of the curve.
They really were. And that 50-year foundation has evolved into today's highly advanced designs, like their Super SC line.
Which I imagine just refines all those alloy compositions and geometries to a near-perfect science.
Oh, absolutely.
So if they've solved the physical challenge of making them basically indestructible, the next bottleneck has to be integration. Like, where do you even put a sensor that small?
Anywhere you can imagine, really.
Right, and how many different ways can you practically package a strain gauge? Because the catalog of Interface mini products is massive.
It's huge.
You've got S-type designs, load washers, submersible models, rod ends, miniature torque transducers. I guess the shape is entirely dictated by the extreme environment it has to survive in.
Precisely. Let's look at the S-type versus the submersible model, for example.
I was actually wondering about that. Here's where it gets really interesting. Why would an engineer specify a tiny submersible sensor versus an S-type?
Well, it comes down to the direction of the force and the surrounding environment. An S-type load cell is, well, it's literally shaped like the letter S.
Right.
That specific geometry is brilliant because it acts like an inline spring. It allows the center flexure to measure tension when things are being pulled apart, and compression when things are being pushed together.
And it does both with equal accuracy.
Yep. With equal accuracy. It's perfect for something hanging in a dry room, like a patient lift in a hospital or a material testing rig.
Okay, that makes sense.
But if you take that S-type and put it 2 miles underwater on a deep-sea drilling rig...
Oh, the pressure would be insane.
Exactly. The crushing hydrostatic pressure of the ocean pushes on it from all sides equally. That would corrupt the data and potentially just destroy the sensor.
So a submersible load cell has to be structurally compensated to ignore the pressure of the ocean.
Right.
And only measure the mechanical force of the drill itself.
Exactly. They are hermetically sealed, usually in heavy stainless steel, and internally pressurized or potted.
So the extreme environmental pressure becomes a total non-factor.
Yes. And this raises an important question, As we move across industries, how do these different form factors actually change the fundamental operation of the machines they're attached to?
Oh, let's take the medical field. Prosthetics is a huge one.
Absolutely.
We are finally moving past the era of static mechanical prosthetics into fully actuated robotic limbs.
And that transition relies heavily on closed-loop control systems. You see, a standard electric motor is inherently blind.
Blind how?
Well, it knows how much current it's drawing, but it doesn't actually know how hard it's gripping a physical object until the motor physically bogs down and stalls out.
Oh, I see.
So in a prosthetic hand, waiting for the motor to stall means you've already crushed the paper coffee cup you were trying to hold.
Which is where the miniature load cell comes in. It provides the feedback loop.
Exactly. By integrating an Interface mini load button or load washer directly into the finger joints or the motor drive of the prosthetic, you introduce millisecond latency PID feedback.
Proportional integral derivative control, right?
Yes, exactly. The sensor is reading the physical resistance hundreds of times a second and telling the motor to dynamically adjust its torque.
Wow.
It allows the user to have natural force feedback movement.
Well, wait, I'm imagining the engineering nightmare of running microvolt electrical signals from a strain gauge through a moving robotic limb.
It's not easy.
Right, especially one that is heavily generating its own electrical noise from all those motors. How do you maintain the signal-to-noise ratio?
That is the exact challenge. If the electrical noise from the motor drowns out the tiny voltage change from the Wheatstone bridge, the hand jerks or just drops the item entirely.
Which would be terrible. So how do they fix it?
Miniature force sensors overcome this by using highly shielded cabling, and often by putting the signal amplifier directly inside or immediately adjacent to the sensor housing.
Oh, so they boost the signal before it even travels.
Exactly. By amplifying the signal right at the source, it becomes robust enough to travel through the noisy environment of a robotic arm without degrading.
That is so smart. And that exact same principle applies to surgical robotics, right?
It does, yes.
I was reading about how they use these miniature sensors in Da Vinci-style surgical robots. If a doctor is remotely operating robotic arms inside a patient's abdomen, they lose their physical sense of touch.
Which is terrifying if you're dealing with, delicate blood vessels.
Yeah, one wrong move and it's a disaster.
Exactly. So miniature load cells are integrated directly into the grip mechanism of the surgical tools. They measure the exact resistance of the tissue being manipulated.
And then they relay that data back to the surgeon.
Right back to the surgeon's console,
Yeah.
often translating it into haptic feedback. So the doctor can actually feel the density of the tissue through the controls.
That's mind-blowing.
It really is. The sensors also play a critical role in testing the flexibility of catheters. As a catheter navigates the complex curves of a human artery, engineers use miniature force sensors during the R&D phase to measure the exact insertion force.
To ensure the catheter won't puncture a vessel wall.
Precisely.
Okay, so you take that incredible life and death delicacy of the medical field,
Yeah.
and then you apply the exact same fundamental sensor technology to heavy aerospace engineering. Like, you go from the grip strength of a surgical tool to validating the landing gear of a commercial airliner.
It's quite the leap. And in aerospace, the constraints are completely different. You're dealing with massive forces, but you have insanely strict weight budgets. Every single gram matters.
Right, you can't just bolt a 40-pound industrial sensor onto an aircraft wing to measure aerodynamic stress during a test flight.
No, absolutely not.
You need a sensor that weighs ounces but can read thousands of pounds.
Right, and you're also dealing with dynamic shock loads, not just static weight. Think about an aircraft hitting the runway.
Yeah, that isn't a slow, gentle application of force.
No, it is a violent, instantaneous mechanical shock. Fatigue-rated miniature load cells are embedded into the landing gear testing rigs to validate the structural integrity under these dynamic impacts.
Wow.
These sensors are specifically designed to survive millions of extreme compression cycles without suffering from metal fatigue or hysteresis.
Hysteresis, that's when a sensor fails to return precisely to zero after the load is removed, right?
Exactly. And it's not just testing, it's assembly too. The assembly of an aircraft requires thousands of bolts.
Yeah.
And the torque on every single one of them has to be mathematically perfect.
Because if you over-tighten a bolt on an airframe, you induce microscopic stress fractures in the surrounding metal.
Yes. And if you under-tighten it, the high-frequency vibration of the jet engines will rattle it loose in midair.
Neither of which you want.
Definitely not.
Yeah.
So miniature torque transducers, which are a specialized form of load cell designed to measure rotational force rather than linear push or pull, are integrated directly into the fastening tools.
Oh, so the tool itself knows when to stop.
Exactly. They ensure that the exact perfect amount of rotational force is applied, stopping the tool automatically the millisecond the target torque is reached.
It really highlights how these sensors are basically the silent arbiters of safety across basically every major industry.
They really are.
And speaking of safety, there is an application that I guarantee everyone listening to this has interacted with, probably without even realizing it.
Oh, I know what you're going to say. Power windows in modern cars.
Yes, when you roll up a car window and your hand or a kid's hand is in the way, the window instantly stops and reverses.
The pinch force measurement system.
Right. I always assumed that was just the car's computer noticing that the electric motor was working too hard.
Yeah.
Or maybe some kind of optical beam. But you are saying it's direct force measurement.
Well, using the motor's current draw is a method, but it's fundamentally flawed because it is delayed.
Oh, so by the time the motor registers a spike in electrical current from bogging down?
The window has already applied a potentially dangerous amount of pressure to the obstruction.
That makes sense.
Yeah, to comply with strict international safety standards, automotive engineers use miniature load cells to rigorously test, calibrate, and validate the actual mechanical pinch force.
But wait, how does the system know the difference between a child's hand in the window and, say, the friction of the window sliding up the track on a really cold morning?
Or hitting a pothole.
Yeah. Or the car hitting a massive pothole while the window is rolling up. Wouldn't a pothole register as a spike in force?
It absolutely does. And this is where the mechanical sensor data meets advanced software. The miniature load cells provide incredibly high-resolution data during the engineering phase, which allows developers to train machine learning algorithms.
Oh, so the software learns what different impacts look like.
Exactly. The algorithm learns to look at the signature of the force. A pothole creates a sharp, high-frequency spike in the data. Ice on the window track creates a slow, steady, linear increase in drag.
But a hand being squeezed
Has a very specific nonlinear compression curve.
Wow.
Because the miniature load cells capture that mechanical data with millisecond precision, the car's computer can instantly distinguish between a bumpy road and a safety hazard, and it reverses the motor before an injury occurs.
Which perfectly transitions us into the macro trend here. We are talking about algorithms analyzing force signatures. If we look at the evolution of Interface Mini products, they aren't just getting smaller and more accurate.
No, not at all.
The entire role of the load cell is fundamentally shifting. We are moving away from passive measurement and into active autonomous control.
If we connect this to the bigger picture, the sensor is no longer just a data logger. It is becoming the active nervous system of smart manufacturing.
I love that nervous system analogy. Think about the human reflex arc. If you accidentally touch a hot stove, your brain doesn't have to consciously process the heat, think about the danger, and send a command to your arm to move.
Right, that would be too slow.
Exactly. The nerve endings in your skin detect the extreme stimulus and trigger a reflex arc in your spinal cord that pulls your hand back instantly, bypassing the central processor entirely. We are essentially giving industrial machinery that exact same reflex arc.
That is an incredibly accurate way to frame it. Traditionally, automated machinery is deaf and blind. A robotic arm on an assembly line is programmed to move from point A to point B. If a part is misaligned on the conveyor belt, the traditional robot doesn't know. It just keeps pushing with all of its hydraulic might until the part shatters, or the robot's own joints snap.
Well, when you embed a miniature force sensor directly into the end effector, the hand of the robot, it instantly feels that abnormal resistance.
Exactly. And because the sensor is tied into the closed-loop control system we talked about earlier, it doesn't need to alert a human operator and wait for permission to stop.
It has a reflex arc.
Yes, it detects the anomalous spike in force and instantly halts or redirects its path, autonomously preventing a catastrophic failure.
And this is the absolute foundation of predictive maintenance, isn't it? Like, it's not just about reacting to immediate crashes, it's about seeing the microscopic trends over time.
Precisely. Let's say you have an automated stamping press manufacturing metal brackets. Day one, the embedded miniature load cell records that it takes exactly 1,000 pounds of force to stamp the perfect bracket.
Okay.
But over the course of 3 weeks, the data shows that force creeping up 1,010 pounds, 4,030 pounds, 1,050 pounds.
Well, the bracket is the same, so the machine itself must be changing.
Right. The system detects that micro trend. It knows the cutting die is becoming dull, or the hydraulic bearings are losing lubrication.
So it flags it.
Yeah, it triggers a localized maintenance alert long before the machine actually breaks down or starts producing defective, out-of-tolerance parts.
You avoid massive amounts of costly production downtime, all because a sensor the size of a coin noticed a 3% variance in physical force. That's incredible.
It's game-changing. And beyond protecting the machinery, this real-time active control is the only way we can safely integrate robots into human workspaces.
Oh, you're talking about cobots, collaborative robots.
Exactly.
Right, because the idea of a heavy, fast-moving industrial robot working shoulder to shoulder with a human factory worker, that sounds like an absolute liability nightmare if that robot doesn't have a highly tuned sense of its own physical strength.
It would be a nightmare. And that collaboration is entirely enabled by miniature load cells. A cobot is covered in these sensors, specifically at its joints and its contact points.
It has to instantly, flawlessly know if the physical resistance it's encountering is the heavy car door it's supposed to be holding, or the shoulder of the human worker who accidentally stepped into its path.
Yes. The high-resolution, zero-latency data from those load cells allows the cobot to instantly freeze or pull back upon unexpected human contact, preventing injury. The sensors are the bridge that makes human-machine collaboration possible.
So what does this all mean? We started out by looking at this mind-bending paradox. Technology is constantly shrinking, but the physical forces of the universe, the 50,000 pounds of weight, the extreme torque, the heavy shock loads, those are not shrinking at all.
Not one bit.
And what we've discovered is that interface mini-load cells are basically the hidden mechanism solving that exact paradox.
They are the invisible infrastructure bridging the digital and physical worlds.
Exactly. Whether it's an S-type sensor hanging a patient lift, a hermetically sealed load washer 2 miles underwater, or a hyperfast torque transducer assembling an aircraft engine. These miniature devices provide the rugged reliability and the microscopic precision required to measure and control reality. They give the delicate circuitry of modern tech the ability to wrestle with the heavy physical demands of the real world.
They really do. And I think the vital takeaway for you listening to this is recognizing that as the global demand for AI, machine learning, and advanced automation skyrockets, software alone just isn't enough.
Right, the software needs input.
Exactly. An algorithm is completely useless without accurate physical data. These tiny, highly engineered sensors aren't just accessories to smart systems, they are the essential enablers. We simply cannot build the autonomous, intelligent infrastructure of tomorrow without the capability to intimately understand and control the physical forces of today.
It fundamentally changes how you view the built environment. Which leaves me with a final thought for you to ponder as you go about your day.
Oh, I'm ready.
We've explored how embedding these miniature load cells is successfully turning huge, passive industrial machinery into smart systems that can actually feel and autonomously react to pressure. But as this technology continues to scale, shrink, and integrate into consumer-level manufacturing, how will our day-to-day relationship with everyday objects change?
That's interesting.
Imagine a near future where the basic things we touch, like our keyboards, our kitchen appliances, the steering wheels of our cars, our furniture, start actively, physically adapting in real time to the exact unique force of our individual interactions. What happens when the inanimate world around you finally learns how to feel your touch?
It is a genuinely profound future to consider.
It really is. Thanks for joining us for this deep dive into precision force measurement and the engineering behind Interface Mini products. Keep questioning the invisible systems around you, and we'll catch you on the next one.